Thank you for the introduction, possibility to be here and give a talk. And yes, and I will be talking about, as the title says, about tracking dynamical features of isolated invariant sets. So if you were hour ago in the other room, you have heard a very similar thing that was described by Ryan. So this is a very related topic to what Ryan explained, and also to the talks that we had in the morning, because we'll be still in the realm of multivector fields. And this paper is a joint work with Tamadej, with Mrozek, Ryan Slechta, and me. Okay, so let me start with the picture. So first, I wanted to make this distinction in comparison to what Ryan described us before, because both problems or both questions are very, very close to each other. So in the previous talk, our setting was that we were interested in a specific region of the faces. And what we were trying to do was to describe and analyze what is going on with the invariant part of the regional inter. So this isolating neighborhood N that we have on this picture. So if our dynamical system would change, then we could notice some difference in our region. So for example, right now nothing has changed from the perspective of Conley index, but in the next step, this saddle that was previously in this region could escape. So using this technique that we saw before, we would obtain the information that at the beginning we had saddle-like structure inside this region, but after some time it left, and there is nothing interesting dynamically inside, because right now we have only this regular flow inside this region. So yeah, so that was the previous problem that we had, or the previous question that we tried to answer. Right now our question is slightly different. So now we are saying that we are interested in a very particular isolated invariant set. So let's again say we are interested in this saddle, and our goal is to study what will happen with this set S when the dynamical system is evolving. So what we expect to see is to see that this particular saddle is moving through the space, and we would like to get some tools to be able to formalize this transition of a set to, for example, other place of our phase space. I don't have the next slide, but we could imagine that after, if we push this evolution further, this saddle S could collide with this another saddle, and we would go through some bifurcation-like event, and we would like to also detect such a moment. But I will come back to this later. And as Thomas in the morning mentioned, we are building this theory of multivector fields, and it is inspired by continuous dynamical systems. And in this work, we tried to translate another concept from continuous world to the settings of multivectors. And the notion that we are particularly interested in is a continuation. So here we have, let's say, simplified definition of continuation is. So if we have, suppose that we have this parameterized family of flows, and we would like to say that two isolated invariant sets, SA and SB, are actually the same isolated invariant sets. Or we would like to say that SB is a natural successor of SA that we have seen before. Because from the picture, it is natural for us that this subtle is the same subtle as this one, but it just moved through this space. So this continuation captures this idea of how we can we relate to isolated invariant sets. And to say that two isolated invariant sets are related by continuation, we have to be able to construct the sequence of isolating neighborhoods that satisfies those conditions. And maybe instead of going through those conditions, let's see this definition in the picture. So the idea is that we are starting with subtle. We construct isolated neighborhood around it, and we let our dynamical system to evolve. And at the moment where we are close to lose the isolation, we construct new isolating neighborhood, and again we let dynamical system to evolve, and we continue this this procedure. And if we are able to transfer isolated invariant set from one place, or we can transport one isolated invariant set to another, then we say that they are related by continuation. So after conditional steps, we would eventually get to this point, and by this definition, those subtles are related by continuation. Continuation may fail because we can imagine that if those 2 points would collide, then exactly at the moment of collision, we won't be able to keep those subtles separated, isolated. Okay. So now we have. Okay, so this was definition from continuous word. Now we want to translate it to combinatorial word. So multivectors were already defined today a few times. So let me give you another maybe intuitive point of view on how we can think of multivectors. And I use a lot of those cartoonish pictures, but treat those continuous flow lines more as an intuition, not as a yeah. From now on, we are in the combinatorial world, so they are just there to give us intuition how the flow more or less works in a particular case. So you can think of multivector fields as a partition of your phase space into kind of dynamical black boxes, and those dynamical black boxes are of the specific form, namely they are locally closed, which in other words means that locally closed set is a set such that only a closed part of the boundary is missing. And the interpretation of that you get also from the formal definition is that what's the dynamical interpretation of this partition? So the solid part of the boundary represents represents the part of the boundary where the flow can enter one of the block. The missing part of the boundary represents the part of the block through which we can escape. And using this instruction, we can build this directed graph that actually summarizes or captures this combinatorial flow that we get from multivectors. Okay, so as has been said already, those black boxes can be seen as a kind of Warszawski sets or isolating blocks. So we distinguish two types of multivectors. The ones that has non-trivial relative homologies of the set itself relatively to the exit part. And those are critical because by the Warszawski principle, we know that if we encounter that kind of set, there must be something invariant inside. So by looking at those black boxes, we don't know what is going on inside, we just know what is going on the boundary. But just by looking at the boundary, we, for example, know that this orange cell represents something invariant. In particular, it represents something that behaves like repelling a stationary point. Okay, and I have more slides, but I will skip them. I have them to make the presentation complete. If someone would like to take a look into this, more formal definition is that multivector field is just a partition of the space into locally closed subsets. This is basically the same, but we have a general definition in the settings of any finite logical space. And formally, this combinatorial flow is defined as a this multivariate map that defines flow. Is a multivariate map which says that from every point we can go to any other point with the same multivector, or we can go to any point in the closure. So in terms of posets, we can go always we can go down with the posets with the phase relation, or we can go to any other point with the same multivector. Okay, and exactly the paths in this graph are our solutions of this combinatorial vector field. These notions will be helpful later. So we distinguish a kind of sets which we call decompatible. So we say that A is decompatible with, we can express it as a union of multivectors. And we also have this notion of those triangular braces, which denotes, which we call VHAL, which means the minimal decompatible and locally closed set containing set A. Okay, and yeah, as I said, we have solutions for our combinatorial system, so it can be interpreted exactly as a B-infinite path in this graph that summarizes the dynamics, but we distinguish a special kind of spool solutions, which we call essential solutions. So they capture, we distinguish them because they capture the essential say, part of the dynamics that we observe in here. So basically, essential solution means a solution that the infinite solution that does not stack for an infinite time, either in future or in the past, in a single regular multivector. So, for example, we can go around a multiple regular multivectors for infinity, or we can stack inside a critical multivector, but we cannot stay inside a single multivector that is regular for infinite time. Okay, and using essential solution, we define invariant parts. So basically, invariant part or invariant set is a set such that for every point in that set, we can build an infinite solution that stays inside. And we have a notion of isolation here, which is weaker than in classical settings, but those two properties are satisfied. So we have this is kind of weak isolation. So basically, isolation here means that if we escape, the first condition says that if we escape our isolated invariant set, we cannot escape it to N, to this isolated neighborhood and come back. And other thing that does not allow is to escape invariant set without getting through the N. But the difference is that isolated invariant set doesn't have to be inside the interior of this isolating neighborhood. Okay, and the crucial concept that we need later is the notion of index pair, which we use to define Conley index, our homological descriptor of isolated invariant sets. Conley index will capture the dynamical nature of isolated invariant sets. And those index pairs are defined as a pair of closed sets that satisfy those three conditions, which in short means the first condition says that we cannot escape index pair without going through the second set E, which is an exit set. Second condition say that we cannot retreat, meaning that if we are already in the set E, we cannot go back to the main part of P. And the third condition says that our isolated invariant set for which we build this index pair is the invariant part of the difference of these two sets. And those index pairs has a property that any two index pairs for one particular isolated invariance S will induce exactly the same relative homologies, which are so this means that Conley index is well defined. It does not depend on the choice of an index pair. Okay, and so we're moving to this main part. So if you were on the talk by Ryan, you notice that the standard way of building this persistence of Conley index for the dynamical system that changes was by intersecting index pairs. But if our dynamical system changes too much, then a lot of unexpected things might happen. So I think we decided to make a little step back and to focus and to really try to see what is the minimal step that we can have in the combinatorial world. So this way we started studying something that I called here combinatorial perturbation. So what's the minimal thing that might happen in the world of multivectors? So the top line represents a continuous dynamical system on the line, and both lower lows are just multivector fields, just drawn in different way. So if you would like to model with multivectors this continuous dynamical system, then we can see that sometimes nothing would change in point moves exactly through this vertex C. To model this properly, we would have to glue those two multivectors together. When this point moves further, then we would like to split again this multivector to have this, let's say, compatible model. So yeah, so behind this picture, there is this intuition that the simplest thing that you can do to multivector field is to refine some multivector. So one of the operations is to split one multivector exactly into two smaller multivectors, or you have this reverse operation when you just glue two multivectors into a bigger one. And we refer to those two operations as atomic rearrangements. In one direction you have refinement, other way around you have atomic coarsening. And you can play with this idea. You can actually build a topological space of all multivector fields for a given space. This is the simplest example. This is the topological space of all multivector fields when you have just a space of two edges. And we plan to exploit this idea in the future, but for now, I just wanted to put this picture here. Yeah, but interesting thing is that you can introduce a topology on that space. Okay, so now we are getting to this continuation in combinatorial settings. So we came up with this definition that translates the definition that we saw at the beginning. So the idea is very similar, but instead of what is the difference? One of the differences is that instead of parameterized family of flows, we have a sequence of multivector fields that are such that every two consecutive multivector fields are related by atomic rearrangement. Or in terms of this finite vertical space of all multivector fields, is just is a tensor in that space. So we have those sequence of atomic rearrangements, and we say that two isolated invariant sets are related by continuation if we can find, if for every S, or let's say for S1, if we can find an index pair. So we are using index pairs instead of isolated neighborhoods here, because isolated neighborhoods in multivector fields are does not uniquely determine the thing that is isolated. Index pairs do that. Index pair uniquely determines what is the isolated invariant set inside. So yeah, so to have this continuation for Si, we require that we can find an index pair that is both a valid index pair for our current multivector field and the next one. So now we want to build this sequence of those connecting index pairs that will transform one isolated invariant set into the other. So let's do it again. Let's go through this definition again by this picture, and also here I want to mention that our goal is not to answer the question whether two isolated invariant sets are related by the continuation, but our question for now is tracking of our initial S0, So the problem that we try to face is we are starting with a given isolated invariant set, and then we want to study what will happen with it in the future. Continuation is not unique because sometimes you can have choices in which direction you continue, but we argue that that the way we are doing it is kind of canonical. Okay, so what's the strategy here? So we have given a sequence of multivector fields related by atomic rearrangements, and we are given our initial isolated invariant set, and we are asking what is the future of it. So the strategy is to build the minimal index pair that is a valid index pair for V0 and S0, but is also a valid index pair for V1. And when we build this index pair, then it will uniquely determine what S1 should be. So we get to another dynamical system, and we ask you this question again, and we can build this minimal index pair that is valid for both multivector fields, and we get S2, and we continue that until we can. And yeah, so this is a strategy and also kind of visualization of this combinatorial definition of continuation. Sorry for this leftover. Okay, and this is, we call it the tracking protocol. So these are exactly the instructions that you have to follow to get those natural successors of your isolated invariant sets when the multivector field is changing by those atomic rearrangements. So we don't have to go in details through all of those points. I will just more or less what I want to point out is okay. So the first point. So every point corresponds to a different case. So in different cases, there's another receive for constructing this minimal index pair I was talking about. So the first case is the simplest one. So whenever we encounter an atomic refinement, we just take and isolate the invariant part of our current isolated invariant set, but compute it for the following multivector field. So this is the simplest case. And also, yeah. So for when you encounter atomic refinement, we can always find the following isolated inferences. Points 2, 3, and 4 corresponds to atomic coarsening, so to the situation where two multivectors gets merged together. And point 2 refers to the situation when merging happens inside our S. Point 3 corresponds to the situation where merging happens somewhere outside of our S. And the most problematic point 4 corresponds when we merge two multivectors where one is inside our S and one is outside. And it is problematic because this is the only case when continuation may fail. So in particular, this theorem 13 says that this theorem, all of those theorems justifies this protocol, that indeed following them we will get the next isolated invariant set in this continuation sequence. But theorem 13 also states that if we are not able continuing using this protocol, then it is impossible at all to go further. Meaning that we are encountering this bifurcation-like event in multivector. Okay, so this is again a picture how this would look like, but in terms of multivector fields. So we are starting with some multivector that represents this saddle, and when our dynamical system is changing, we maybe want to rearrange multivectors. So at some point, we would merge some multivectors together to get bigger S. This was a case 4 where we merged multivector from our S and something from outside. After some time, we might split the multivectors. This is case 1. This is another splitting. So again, case 1. And there also might happen something outside of our isolated invariant set, but this is kind of case 3, meaning that whatever is happening outside of our S, it never affects our S, our isolated invariant set of interest. And okay, here we have two theorems that justifies or explains why we claim that our choices that we make are canonic. Yeah, they simply say that the S prime, the new isolated invariant set that we get, is the most similar one to the one that we had previously. So the most similar, for example, in terms of number of simplices. So we claim that the choice that we make is the most natural. Okay, and we have this continuation, but we now want to put it into a language of persistence. So what we have now so far is a sequence of connecting index pairs. But to have persistence, we need to build something like this filtration. So the strategy is that we connect two connecting index pairs through a canonical index pair for a given isolated invariant set. And this canonical index pair, because you can see that those three index pairs are actually all index pairs for the single S1 in this example. So we have three index pairs. We know that they are index pairs for a single isolated invariant set, and we want to and we know that all of them induce the same homology. So now what we want to connect them properly, so to make sure that the generators that they induce don't get mixed up, let's say. So yeah, so this inclusion that was above is a lie, because behind this inclusion actually sits this sequence of inclusions, and behind the second one sits the symmetric sequence of inclusions. And so this does not look very well. This is a lot of work to connect two index pairs, but I think I have too little time to explain exactly that this sequence of inclusion is actually not that terrifying as it looks like. In order to explain what is going on here, I would have to introduce this concept of index pair in isolating set N. Maybe I will just skip that. The point is that this sequence of inclusions in general induces a sequence of isomorphism. So so we are able to connect two index pairs with a sequence of isomorphism. So we know that we know that generators from the index pair was translated into say the same generators, corresponding generators with the second index pair. And the other remark is that this is the most general recipe how to connect them, but in a lot of cases this sequence will get simplified a lot. Okay, so we can connect this long sequence of all index pairs connected, and we have this theorem that says that this huge sequence that we constructed actually is quite boring, meaning that the persistence homology that we compute for it is actually a few bars, a few full bars, where every bar corresponds to the generator in the Conley index of our initial isolated invariant set. So yes, this is what we get, but this is what we expected, because continuation means, yeah, by continuation we wanted to preserve dynamical features of the isolated invariant set that we are tracking. So this is okay, but we can go further, and as I mentioned, in this point far, in this one case of our tracking protocol, we may fail to continue. But we suggested steps that we can follow alternatively in this case, so we can continue actually, because the problem there was that we were not able to find an index pair that is a valid index pair for our current multivector field in the following part. But we can still sometimes construct an isolating set for our isolated invariant set that is still an isolated invariant set in the following multivector fit. And this is the case here when those two saddles are getting close to each other, and there is no possible continuation, because from the perspective of our combinatorial resolution, we can't separate them or isolate them no more. So what will happen is that we would merge those two multivectors together to get this big representation of the monkey cell. And using these additional steps that we had on the previous slide, we would capture this transition, this merge of two isolated invariant sets, and we again claim that the choice that we make to continue this tracking is a canonical one. And we have another sequence of inclusions that will allow us to apply in the end this persistence homology algorithm. Now these are not necessarily inclusions, and we will notice the changes in the Conley index of the isolated invariant set that we track. Okay, let me skip that because I'm out of time. So summarizing this, using this tracking protocol, we are able to, following the isolated invariant set of choice, and using persistence homology, or we can use persistence barcode as a kind of timeline, what is going on with our Conley index when the dynamical system evolves. So we'd get a picture like this, and at some point this protocol would notice that new generator appeared, and we can interpret it as a moment where our isolated invariant set goes through some kind of combinatorial bifurcation. And yeah, and I think I will stop here. Thank you.
So it seems that you try to partition your space according to vector field that is given.
The partition of a space we assume here is an input to this protocol, because maybe that was misleading. Maybe those pictures were misleading instead of helping, because the assumption is that we are given a sequence of multivector fields.
Okay, so a sequence of partitions.
A sequence of partitions that differ by this atomic perturbation, atomic rearrangement. So this means that if we are in V1 and we move to V2, this means that only one multivector, for example, in V1 get split into two multivectors. Or there's the other possibility that two multivectors only get merged into a single one.
But so the theory that you have developed tells you when the sequence of multivectors has been well chosen, or Is there something that I'm missing? Because
those sequence of multivector fields represents is a, let's say, combinatorial version of a parameterized flow. Let's say that way.
But what I cannot see is how you decide how you choose the partition at each step.
So if I may add a comment. For the theory, it doesn't matter where these partitions come from. So you can even take them randomly,
Okay.
and you probably get not very interesting answer, which will just tell you that nothing continues because they are not related. So the closer they are one to the other, the more you get out of it in practice. Probably these partitions will come from some simulation of really changing flow, where you try, for instance, there may be different strategies to guarantee the transversality as how shown in the figure. But so let's say you really have a sequence, a parameterized differential equation. Yes, you discretize it for each point in the sequence of these fields. You pick up a triangulation and you look where you have transversality, where you have no transversality, you remove this edge, you get a partition and a multivector field, and you expect that since it came from some real application, it should be better. Yes. But for the theory, it doesn't matter where this come from. Probably the results will be not interesting if you take them purely random.
Okay, so the inference that if the partition that has been well chosen, something interesting will get out of it.
There is no theorem like that yet, because this is not tied to any concrete differential equations. That would be a result along the one which was very difficult we got with Thomas, that actually in the spirit, which is not done here, that given such a sequence, you can really model it by a concrete flow. This is maybe an ambitious goal for the future. For the moment, it's just to set up that we really can speak about persistence in this setting.
So no other question, we can just figure it out.